A common type of problem in calculus is to evaluate the limit of some function where there's a discontinuity. Again, we can't just plug in the value because the function is discontinuous, so there is a break in it, but the limit can tell us where the function would have ended up were it not for that hole. Let's take a look at this example here. G of x is equal to x squared minus 4 over x plus 2. For this function, I think we can all agree that if x is equal to negative 2, well then if we plug that in, we'd get negative 2 squared minus 4 over negative 2 plus 2, and here we'd get a divide by 0. As soon as we see that, that means that g of negative 2 is undefined. And that means we most likely have an asymptote or a hole in this function. The limit will help us distinguish which of those two cases is actually the fact, whether it's a hole or whether it's an asymptote. Let's take a look at how we might evaluate that limit. What is the function doing as x approaches negative 2? If x squared minus 4 over x plus 2 is our function. Well, recall the important ingredient about a limit. X approaching negative 2 means explicitly x is not equal to negative 2. We're going to look everywhere but at that particular point. So the syntax we're going to use is to keep this limit here as our first phrase in the expression, because that's what we want to evaluate. But before we can evaluate it, we need to somehow take care of this dividing by 0 problem. In this particular case, we look at our x squared minus 4 and recognize it as something we can factor. It's a difference of squares. X plus 2, x minus 2 multiplies out to x squared minus 4. And then we see that we've got a common factor. Now, you might think, well, why is it okay to divide by that? Because we're going to be letting this equal 0. Remember, with a limit, we're never actually going to have x equals negative 2. We're going to see what happens when we get close to it. So for those who are concerned about dividing top and bottom both by 0, we're never actually doing that. It's a slightly different technique, and it makes all the difference in terms of what we're allowed to do. Once we've done that simplification of canceling the like terms in the numerator and denominator, then we have something now that is continuous. So this is not continuous at x equals 2, x equals negative 2, sorry. This one is. And so we can just sub in x equals negative 2. Here we could not just sub in x equals negative 2 because we got our division by 0 problem. Here we can, so we get negative 2, that's our x being subbed in, minus another 2 equals negative 4. So what do we think this looks like now? Without knowing too much about the function, when we go to negative 2, there's going to be an open hole there, and the graph is going to do something around it, but it's going to be at a height of negative 4. As the graph approaches in from the left or the right, we're going to have that value approaching negative 4, but there's going to be a hole there because we can't actually plug in x equals negative 2. So that's what this kind of calculation gives us. We know it's discontinuous, there's a hole, but we know that the function's well behaved. It actually converges towards a particular value as we get closer and closer to that hole in the function. Sometimes we have functions that are defined in a piecewise way, and so we have to think about that last idea I just mentioned, the left, coming from the right, coming from each side of a hole, what happens? And especially with piecewise functions, different things are happening on the left and on the right of some breakpoint, so we might have a different kind of discontinuity there. All right, let's first study the easy cases. On what intervals is the function clearly continuous? Well, if x is less than 1, then this function here applies. and it's continuous by itself on x less than 1. So for x less than 1, we have a nice linear function. That's definitely continuous. Same thing here for x greater than 1. This function is clearly continuous. It's just a parabola. And so there's some combination here of some linear function up to x equals 1, and then some parabola. And now our question is, do these two things line up or not as we transition between the two areas? Then the point of concern, of course, would be at that transition when x equals 1. So we're going to have to study that a little more carefully. That decision about whether a function is continuous or not, we realize that the limit question is actually a little more subtle, or can be a little more subtle in some cases, because we have different sides of a gap. And we're going to need some technology to handle that. So what we do here is go back to our limit. That's where the challenge comes in here, is how do we define the limit? Well, by default, when we say x approaches some value and ask what the limit is, we get that value if and only if the right hand and left hand limits exist and are both equal. So similar to continuity, but a slight difference in that we're talking about directions of approach here. And just to elaborate on some of these symbols, this x with c with a plus here implies from higher values. So if we're thinking about this on a real line, if we had some value c, and this is our x-axis here, when we come from above, that would be c from the right in our traditional way of laying this out, and the plus just means we're coming from high values going down towards c. If we wanted to go up from the left, that would be x approaches c from smaller values, or we'd have a minus sign, that's a little exponent there, from smaller or lower values. All right, so it's a new notation that we have to use, but we'll see that it's fairly intuitive when we come to applying it to especially piecewise functions. In this particular example, if we're going to ask, does the limit as x approaches 1 of this function exist? And if so, what is its value? Well, the limit as x approaches 1 of h of x is only defined if both one-sided limits exist. Notice we didn't worry about this before. Sorry, exist and are equal. We didn't worry about this before because our functions were always the same on both sides. We used the same formula on both sides. Here, if we talk about the limit as x approaches 1 with a plus, again, reminder, from the right, or what's built into that is x larger than 1. These are all the same statement. X approaching 1 from the plus side is from the right, or then values must be larger than 1. So what we can say with this limit is that x is always going to be positive. So when I ask, well, what is happening to h? What is happening to h when x is larger than 1? Well, this is the formula we would use for all of that side. And so we can sub in the limit is x goes to 1 of x squared minus 1. We can put the plus in if we like, or if we don't like. This function will do the same thing regardless of whether we come from the left or right, because now we've isolated already the branch or the half of the function that we're interested in, and here's the formula that goes with it. So this correlation here, this substitution happens because we're coming from the right. If you're thinking ahead, you'd say, hey, what's going to happen when I come from the left? Well, x will be less than 1 if I'm coming from the left, and we would use the other formula. So let's just note that down here. This would be x greater than 1, and this will be x less than 1 when we come from the left. All right. And so now we see the advantage or the assistance that is provided by having one-sided limits. This is easy to calculate now. Once we've said we're coming from the right, that means we're using only this formula, not some mixture of both. Only this formula, we can just sub in. That's a continuous function. So we can just plug in the value, and we're going to get 1 squared minus 1, which is 0. On the other side, as x approaches 1 from the left is how we read that, or x being less than 1, that would be our approach from this direction. Well, let's add our h of x here. What does this function do as x approaches 1 from the left? Here we go up to the top part and use that formula. Why? Because we said we want to only consider x values less than 1. And again, the negative at this point is optional. What we really care about is that we're using this function. Again, this function now by itself is nice and continuous. So the limit evaluation is just plugging in. So we have minus 1 plus 1, which is equal to 0. All right. So both one-sided limits exist. And are equal. That's the important part. And that lets us say that the limit as x goes to 1, this is the two-sided version now, or what we used to call just the regular limit of h of x, well, it's going to exist, but more particularly, it's going to equal 0. So, if we have a function where there's a piecewise definition, and so there's an obvious transition point, what can we say about that? Well, we can say at the transition that it's that the limit exists if both of these functions, both of these limits rather, from the left and from the right, coming in from the left, coming in from the right, agree in their values. What does that tell us about the continuity of this point, of this function at this point? Well, we have that the limit as x approaches 1 of h of x is equal to 0. What else do we need for continuity? So that's the limit. We also need the value at x equals 1. Well, h of 1 is equal to, let's flip back 1 second. When x is equal to 1, we use this function here. So, what if we just plug in x equals 1 into this? We'll plug it x equals 1 into this formula. And so we'd have negative 1 plus 1. And that gives us 0. And so we have that third condition satisfied for continuity. So the limit as x approaches 1 of our function and h of 1 both exist and are equal. The satisfaction of those three criteria tells us that h of x is continuous at x equals 1. The limit exists and it's 0. The function value at that one point exists and is also 0. All those things agree. That means we could draw the curve as one smooth line with our pen. It's actually worth sketching out now what that might look like, because we have the two ingredients, the function on the left, which is given by minus x plus 1, and the function on the right-hand side, which was, let's remind ourselves, x squared minus 1. And what all of this work has told us is that the function has a y value of 0 at this transition point between the two graphs. And I think most of us will recognize the structure here. This is a graph with slope -1, like so. We know one point on it, so we get the basic shape. It would keep going if it weren't for the split definition, if this applied anywhere past x is less than or equal to 1, but it doesn't. So we have the straight line, and then we have a transition to the quadratic, and the quadratic is x squared minus 1, so shifted down by 1, or the classic quadratic y equals x squared shifted down by 1, and after this point it picks up again. And what we see is that we could of course draw this curve as one smooth stroke. It would come down and then would go up. It's made up of two different pieces, but they join seamlessly at the transition point between both graphs. Just to give us more of a range and some ideas of how these things can work or not work, or exist and not exist, let's talk about functions where, both one-side limits exist, but the overall limit does not. That's actually pretty straightforward. Imagine that same example where we had the function coming down and stopping, but then after that, the function was, say, x squared minus 2. So in an open circle here, we have this kind of graph. Here, the limit as x goes to 1 from the left exists. It would be this point here. We'd go down towards that point there. The limit as x goes to 1 from the right would exist. It would be the point we'd end up at following the curve down this branch, but they're not equal. And in that case, of course, we can't say what the limit at the point is because, well, it matters which side you come in on. And if it matters what side, then you have to say what side, etc. It means you can't say the limit, the single limit is. What kind of other artifacts are common? Well, we could have one function coming down like we just saw, and then we might actually have an asymptote. So actually, let's take that out for a second and put an empty circle in the end here. So we could have a graph that's fairly well behaved and then has an asymptote like that. Another case is one we've seen before, the graph of 1 over x, where neither one-sided limit exists, and they're actually differently, they have different infinite limits, which sometimes is important as well. This graph would go off to negative infinity from the left as we approach x equals 0, and it would come towards positive infinity if we came in from the right. So those are a range of different discontinuity types or different limit types when we look at left and right hand behaviors.